आणि मला पाठवायचं असेल.
Thank you, sir. I feel honored to give your introduction. Dr. Kishore Bhoyar, sir, is professor in Department of CSE in Yashwantrao Chauhan College of Engineering. He has completed his PhD from VIT Nagpur. He has published more than 50 plus research papers in reputed national and international journals and conferences. He is working collaborative with research projects on NUNAT national assessment. He has also received grants from MODROPS and RPA schemes of AICCE, also in national and international journals of Singapore and Malaysia. Not only this, he is having the experience of 30 plus years. He is an approved supervisor from PhD in Computer Science and Technology at RTM in Nagpur. Apart from YCCE, he has also worked at Kids Nagpur, and he has organized many training programs and workshops and conferences for faculties. He is a life member of ISTE, professional member of ACM, and associate member of CSI and member of ISCSI Singapore. That's all from my side, sir. I would request you to please start with your. Thank you, sir.
Thank you, madam, for a generous introduction. Good morning, dear participants. Now, in this particular AICTE sponsored FDP, I have taken this particular topic, that is gradient descent algorithm. Now, actually, this algorithm is the backbone of many machine learning techniques, right, including backpropagation algorithm and polynomial regression and so on. So, it is very important to know what is this gradient descent algorithm and how it allows you to optimize parameters of the machine learning model. So, to explain this linear regression model I have selected to explain how the gradient descent algorithm works, because this is the most simple technique, machine learning technique. Now, in statistics, this linear regression is linear approach to modeling. Okay, and it models the relationship between the input variables, one or more input variables, and the output variable. Right. So we call output variable as a scalar response or dependent variable, and one or more explanatory variable. Okay, they are called as independent variables, and they are also called as predictors. Okay. So based on these independent variables, we take some decision. Okay. So if you have a single input variable or independent variable, then it is called as a simple linear regression. And if you are having multiple independent variables on which your output depends, then that is called as a multivariate regression, because there are multiple inputs. Okay. Single input is simple regression, multiple inputs is multivariate regression. Now there are some assumptions about this model. In simple linear regression, we assume that there is a linear relationship between the independent variable x and the dependent variable or output variable y. That is also called as response variable, and the equation is given by y is equal to beta 0 plus v1x plus epsilon. Now you know the equation y is equal to mx plus c. Okay, so it is same thing. Simply here c is beta 0, m is beta 1. Okay, so this is y is equal to m c plus m into x. Now there is one more quantity epsilon, that is the error, that usually we do not talk, but it is worth mentioning. So beta 0 is the y-intercept and beta 1 is the slope, and epsilon represents the error term accounting for the variability in y that is not explained by the linear relation. Now it is very interesting to know why this epsilon is being contributed here. Okay. So linear regression, ideally how it should be, if you have some phenomena, okay, and this is a line, best fit line, and all your points. Suppose I draw all the points on all my observations are on the same line, exactly on the same line. Okay, so this is the ideal case, but this is not the case usually, right? What happens is that your actual reading do not follow this exact linear relationship, but there is some error, right? And this occurs because of different reasons. Okay, ideally it should be exact line, but it is not exact line in practice. Okay, so this is the error term and sources of noise. So epsilon represents the noise in the data basically. Okay, so why the noise is caused? It is because of the human error. It may be because of noisy sensors and environmental factors. It may be because of data transmission error. Suppose you are sending the data from one place to another place, then there may be data transmission errors. Malicious actors. Malicious actors may intentionally introduce noise into the storage, into data to sabotage a machine learning model. So what is the meaning of that? So basically, you might be knowing that machine learning is a domain. It comes in the domain, broad domain of artificial intelligence, right? And what is the difference? Major difference between the your traditional AI and machine learning is that machine learning depends on the data. So data is actually a kind of experience. So how human beings learn? We learn by experience. So the data plays the role of experience, and your model learns from that experiment. So if your data is not good, what will happen? It will, of course, your model that is resulting from this data will not be good. So suppose someone don't want you to implement the machine learning model to the best accuracy because of their own interest. Suppose you go to the doctor and doctor says, if you implement this, then what is my role? So what he will simply do? He will give you wrong data. Now you try whatever you may try. You try the best algorithm, best hyperparameter settings, and everything. You conduct hundreds of experiments and find out the best hyperparameter set for your model. In spite of all those things, you will not get the best model because your experience is wrong. The doctor has given you the wrong data, medical expert. Okay, right? But that is unethical. But it will happen. So if someone wants, some expert wants that his knowledge should not be incorporated into the expert system or into the machine learning model, then he simply will give the wrong data. That is the end of it, right? And this is the, I mean, these people do not do this. Actually, what they do is that if you take a problem in the medical domain and you go to the medical expert, they will simply deny you the data. They say that we are having privacy issues and we cannot share the data. Okay, so many PhD holders that do research in this area, they face this problem. So data is everything because if there is no data, then you cannot train the machine learning model. So that error is because of that. So in statistics, this simple linear regression is a linear regression model with a single independent variable. It concerns two-dimensional sample points with one independent variable and one dependent variable. So this is a simple 2D problem because one input variable and one output variable, right? So you can take a simple example. This is a very simple example, that is prediction of student placement package in your college, okay, or annual salary of the student from the final year CGPA, okay, that you want to do. Okay, so you know that if your college gives good education and your processes are strictly followed, then the CGPA is supposed to represent the intelligence of that student. Okay, and naturally, the more the CGPA, more intelligent should be the student, and hence he should get more salary. So this is a simple reasoning behind this, and you can implement a linear regression model. So you can see here, suppose you take CGPA on x-axis, that is typically we take input variable on this axis, and your y-axis is the output, that is the salary per annum. Okay. Now this is a largely linear phenomena because CGPA is not everything. Maybe there are other factors. What does it mean? Why this is not linear exactly? I mean, it is not a that much linear set of observations here. Why? Because you have considered only CGPA and there are other factors that influence the salary, like maybe the coding skill of the student, maybe the communication skill of the student, and because of that you will not get exact linear relationship, right? So it is occurring because, and you can see some outliers also at that. I mean, some student with maybe very low CGPA like 6 is having very high salary. Okay, you can see the topmost point here, that is called as an outlier. Okay, so there will be some outliers like that. So if such thing happens, it may be that you are not modeling your problem correctly. Maybe there are insufficient number of variables you are taking. Okay, but for our I mean explanation, we will take only a simple linear regression uh, for this particular algorithm. Okay. Now there are closed form solutions available for linear regression. Okay, closed form solution means what? The direct solutions are available. Direct mathematical formula is available to find out the parameters of the model. Okay, so when you say y equal to mx plus c, so or you say what is salary is equal to m is m into what, the CGPA plus some constant c. Okay, so this m and c are called as the parameters of the model. You know that. Okay, m and c are called as parameters of the models, and those you have to find out. So once you find m and c, you get the equation and you can put any. If once you know m and c, now you put any value of CGPA and it will give you what is the predicted salary for that student. So you give the CGPA of the student, you get the predicted salary. Okay, it is very simple. But the main thing is about finding m and c. Now in the closed form solution, these modelable parameters of m and c are given by m can be given by this summation I equal to 1 to n. There are n number of samples, training samples or training examples, okay, or training instances, okay. And what is x bar? X bar is the average of x, y bar is the average of y, okay. So with this you can find out m, and you know that y is equal to mx plus c. So what will happen? C is equal to y minus mx. Okay, where this y bar is what? Is the average, and x bar is the average of y, x bar is the average of x. So you get m as well as c. If you get both, you can construct a equation and directly find out. So this is a closed form solution that does not require any training, and hence it is not a ML solution. It is not a machine learning solution. It is a, I mean, analytical solution directly available in the form of formula. So these are just, this is one more example. So this is about basically some companies there, and the third column, first column shows the year, second column shows how much sale was done for a particular product in million euros, and the third column shows the how much you have spent in how many millions you have spent in advertisement. So advertisement, if you spend more and more amount in advertisement, you are supposed to increase the sales. Okay, sales will increase. That is what is the relationship. So this is a simply a linear relationship, because as this increases, you can see the sales also increases. So you can, I mean, this is one example of linear regression. Okay. Then this is once the same example, we are predicting y, that is the salary from the CGPA of the student, that is x. So once you train the model, you can input some CGPA like 7.2 and you can give the output. So this is just to tell there are many such problems. Okay, you can think of, but if you feel that the relationship is linear between the input and output, then only go for it, right? And in very real problems, the relationship may not be simple linear. That's why you require other non-linear algorithms like maybe polynomial regression and neural networks and so on. Now, gradient descent or steepest descent algorithm. Okay, so basically, our main aim is to study gradient descent algorithm in this lecture, because it is very important and it is backbone of many machine learning algorithm, including backpropagation. So gradient means actually a slope, okay? And descent matlab where the slope is going down, or descent matlab slope is becoming less, right? जैसे descent मतलब उतार बोलते हैं हम उसको, right? Ascent मतलब चढ़ाई, descent मतलब we are going down. Okay, so this is the search strategy used in continuous search basis. Now objective of the gradient descent is to find the model parameters that optimize the objective function, which is called as a loss function, error function, or cost function. These are all the names of the same thing in machine learning. Okay, I have mentioned it because many times you come across these terms. So this error is given by e is equal to 1 by n, I is equal to 0 to n, because there are n examples. Okay, and yi minus y cap cap square. Actually here y bar whatever written, actually it should have been y cap. Okay, so I write this. Okay. Y bar meaning is y average actually, but it is not y average. It is error is equal to 1 by n, because it is the average. Okay, so it is 1 by n. Summation I equal to 0 to n minus 1 we will take, because there are n examples training instances, so that should be n minus 1 here, and yi minus y I cap whole square. Now this yi cap is what? It is a predicted value. Okay, and this yi is actual value. So actual value of the response variable or output. Actual output is y, and what is predicted? Y cap. Then what is the difference? This will be error between the actual value and predicted value. So suppose you have predicted something and actual value is different. So predicted salary is different. Salary predicted by your algorithm is different, and actual salary is given is slightly different. It will not be exactly match. So there is some error. So what should happen? This error should be as minimum as possible. Then your model is correct. Over all the training instances, okay, all the n training instances, this error should be less. So now this error is 1 divided by n, okay, because we are doing average. So this is called as mean squared error. Okay, you might have heard it many times. You are a student of machine learning, or otherwise also you might be knowing it. Mean squared error. Okay, so this is the error. Okay, one more thing I wanted to say here is that what in many books you will find that they will take it as 1 by 2n instead of 1 by n. Now why? Because you will see that in this particular algorithm you need to differentiate this loss function, okay, with respect to model parameters. So in that case, what happens when you differentiate, this 2 in the derivative will come to the, what will happen is when you differentiate, this 2 will be coming here, okay, and this like 2 and 2 gets cancelled, so it becomes simplifies the terms ahead. So that's why they sometimes write 1 by 2 also, but that doesn't make really much difference, because this is the iterative algorithm that will converge. So don't get confused if you say that somewhere it is 1 by 2n, but it should be 1 by n, but for adjustment of derivative terms they are making it 1 by 2n. Okay, so in mathematics, gradient descent, also called as steepest descent, is a first derivative optimization algorithm, first order derivative optimization algorithm for finding a local minimum of a differentiable function. And this differential function is actually an objective function which must be a continuous, okay, differential function. It is the basis for many machine learning algorithms like linear and logistic regression, backpropagation algorithm, etc. So that's why we are studying now, and we are studying this with reference to linear regression because it is easy to understand. And once you understand it, then you will be able to understand many other algorithms. So basic strategy of this algorithm, steepest descent or gradient descent algorithm, is that you have to take steps in the direction of steepest descent. Now what you do when you want to go from the top of the hill, okay, so you might be seeing that I have drawn there the hill, okay. Suppose you want to go down from this place to this place. So if you want to quickly reach to the lowest position, or down the hill if you want to reach, what will you do? You will go in the direction in which direction of the steepest descent, okay. So you will go faster, so where the slope is changing faster in the downward direction, right? So that is basically it. So gradient is a vector, it points in the direction of steepest ascent, but the property of gradient or slope जो gradient vector होता है that points in the direction of steepest ascent actually. Okay, but you want to go in the direction of steepest descent. Okay, so that means you have to go in the negative direction of the gradient, because gradient will point to the upward direction and you want to come to the downward direction. So that's why you take the negative of the gradient. So the gradient is given by a vector whose elements are the partial derivatives of the cost function with respect to the model parameters, right? So now this gradient matlab kya is slope matlab derivative. So if you take the derivative, there are two model parameters, one is slope and another is intercept. So that means if you are having one input variable, how many parameters are there? There are two parameters. If you take two input variables, there will be 2 plus 1, that is 3 parameters. Because one parameter is your the fixed term. Okay, it is your intercept term. Okay, so because of that, you will get one parameter higher. Okay, so you have to take the derivative. For example, if you do the simple linear regression, okay, if there is only one input variable, you have f and c. So you have to differentiate with respect to f as well as with respect to c. So you have to differentiate the cost function with respect to the model parameters. So in this case, there are only two model parameters. So basically, if you see the graph on the left, so error minimization by moving the direction of the steepest descent. Okay. So now you can see the graph in which on the right hand side there are the weights. So this W, okay, W is called as a weight vector. In some books it is written as a theta. Okay, in some books it is written as a beta. Okay, so W is what? It is W0 is one parameter, W1, W2 and so on. Okay, if there are m parameters, then this will be like this, W0, W1, all beta 0, beta 1, beta 2, theta, and or beta 0, beta 1. Different books talks about takes different terms for parameters. So W means parameter. So in this case, in our problem, this W is nothing but for what a vector consisting of two values m and c. Okay, there are two values. Okay, two parameters are there. So the vector has two values here. Okay. So this on this axis there is a weights, say weights. So simply assume, suppose you are having single weight for the time being. Actually, it is a multi-dimensional space, but we are trying to represent it only in single dimensional. Single weight dimension. Okay, just for simplicity. Okay, so this is weights W, and on the that axis, okay, y axis, there is a cost J of W. Naturally, this J of W is a objective function J, which is mean squared error. Okay, typically, and this may be called as J of W or J of theta or J of beta, whatever symbol you take for that. So don't get confused if you are getting theta somewhere. Depends what symbol you take. So here I have taken W, for example. Okay. So what you do, you start from some point. Maybe if you are having a curve here, okay, you may be starting from this particular point, or suppose here you are starting from this particular point, then you are moving in the direction of the steepest descent, okay, or decrease, okay, where your error actually decreases. So you will move to the point, okay, where your error decrements faster, okay. So like that. So when you go in the direction of steepest descent, okay, the gradient direction will be at any point will be upwards, and okay, if you draw the gradient vector at any point, if you draw the tangent that represents the gradient, so it will be pointing towards the upward direction, and we want to move to the downward direction. So you will reach to the point, basically this point, which is the where the error is minimum. Okay, so this is called as a global minimum, and sometimes you may get stuck in the local minimum. Okay, so this is local minimum. You may stuck here, and you have to take some steps, higher steps, in order to come out of the local minimum. So forget about that. So like that, this is a this is called as a error surface. Okay, so you are moving in such a way as to minimize the cost or error. Okay, so wherever you get the minimum cost. So what is the answer now for this? You want to find out the best W. So what you are trying to find out, if for this particular set of data points you want to find out what is the line Is the line like this? Baseline, or is the baseline like this? Whatever it is. So out of many lines, many possible hypotheses, you have to select one which is the best. Okay. So the best line can be found out by using this particular algorithm. So best parameters. So which best parameter you will get? So if you see here, this is the point where your weights will give you the minimum error. So that will be returned as a value of W, that particular point of, at which your error is minimum, that will be returned. Okay. So mathematically the gradient. Okay. So this is the algorithm on the right hand side. Basically, it is written in a more like a neural network form, because W is used in neural network for set of parameters actually, and theta is the most common terminology used in the books. Okay, so I have taken this slide from MIT open source where. Okay, so algorithm is very simple. Initialize the weights randomly. Okay, weights here mean the parameters. So say initially you don't know what is the slope and intercept. So suppose initially my line is something like this, and then slowly I will change the MNC, and maybe next time I will have this line. Okay, next time I will have this line. Next time I will have this line, and finally I will be having the baseline. So this MNC continuously updates, and you get the better and better line every time. Okay. So initially you have to take some random values, so near 0 for the parameters. Okay, and sigma square is the variance of that. You can specify there is a random function. You can specify these parameters there. Okay, mean 0 and variance of sigma square. Okay, that you can specify in the randomization function if you want. Now loop until convergence. So convergence criteria can be different. When to stop the algorithm. Okay, you can say that after so many number of iterations you would like to stop the algorithm, or you can say that I will stop the algorithm only when my error is below a certain threshold, maybe 0.001. So when error drops below 0.001, I will stop the algorithm. Okay. Or you say that M and C doesn't significantly change over the iterations. It almost is still. So the situation will come when the M and C will not change much, or they will remain constant. So that also time you can set the convergence. So loop until the convergence. What you have to do? You have to compute the gradient. So gradient is dou J of W by dou W. Okay, that means whatever is the cost function or error function, that is mean squared error function, that you have to differentiate with respect to W. So why there is a partial derivative here? Because you have to differentiate with respect to all the parameters one by one. So you have to differentiate with respect to first parameter. Okay, because see the model has multiple parameters. Like say here you have two parameters. You have to differentiate with respect to M. Then you have to differentiate with respect to C also. Okay. So you compute the gradient. So gradient, matlab again it is a gradient vector, because there will be multiple components. It is a vector, gradient vector. Why it is called as vector? Because there are multiple components. Okay, because when you differentiate with M, you will get one component. When you differentiate with C, you will get another component, and so on. So you will get a vector. So that's why it is a vector. So compute the gradient. Now update the weights. So how will you update the weights? W is equal to W minus eta into dou J W by dou W. Now what is eta? Eta is called as a learning rate. Now how fast you want to learn? Okay. Then what is this minus sign? Because you want to, because gradient जो है dou J W by dou W, it will point to the steepest ascent direction, and you want to move to the steepest descent direction. That's why there is a minus symbol there. Okay. And what is the importance of learning constant? So say learning constant is also called as a learning rate. So this eta is called as a learning constant or a learning rate. So what is the meaning of this? So many times as a student, what we do sometimes prepare for the exam just one day before night. So that time your learning rate is very high. If the learning rate is very high, then do you learn correctly? No, because you are bound to make mistakes. So slightly, tedious questions or slightly critical question in the exam can lead you to failure, right? Because you are not learned into the depth. You are not learning slowly. So if you learn slowly, that learning will be better. Okay. So, but if you learn too slowly, that is also not good. And if you learn too fast, that is also not good. That means eta should be some optimized value, better value. So basically, the choice of eta is, it depends. You have to go on varying and see what is the best value of eta. Because if you make very high value of eta, your algorithm may learn faster, but it will not may not learn correctly. Okay. So eta you have to select. Okay. So gradient descent involves updating the model parameters in the direction of the negative gradient of the cost function, or negative gradient मतलब slope मतलब derivative. So that means minus eta times dou j w by dou w. So simply you have to go on updating. Now when I say update weights means what? It is written as a single step here, but actually what will happen? Each of the parameters will be updated. Okay. So like m will be updated. Okay. And C will be updated separately. Okay, this all the parameters will be updated individually. So this is written in a vector form. W vector is equal to W minus eta into dou j W by dou W. Okay, but actually you are doing multiple calculations. Okay, for each of the parameters, this equation will hold. Now once the algorithm converges, what you will be returning is the weight, the parameter. Because what is the output of your machine learning program? Can anybody tell me? What is the output of machine learning? When you train the machine learning model, what you get as the output after training? You get the final model parameters. So if I am training the linear regression model, then my final output of this linear algorithm, okay, with a single linear regression, suppose I do, so will be the value of m and c, final values of slope and intercept. That means what is the final value, final line that I get. So this line is expressed as slope and intercept. So that m and c I will get as the output of this algorithm. Final parameters, okay, that we are getting as the output. Okay. So here objective is to minimize the cost function, because we want that point where the error is minimum. And you can see in the graph the point where global minima is there, that point is the minimum. And at that point, whatever are the parameters, weights, that will be returned. Okay. So this is the discussion about the basic algorithm. And here, if you are doing, I have drawn the diagramming three dimensions actually. Now you can see here, I am on one axis, one parameter, right, and C on other axis, and this is the mean squared error. So you can see at this particular point, okay, suppose this is your global minimum. So at this particular point, there is some M and there is some C. So that point we are interested in, where the error is minimum. Okay. So at that point, because error is coming down as you are, and this is the path that is followed by your algorithm, right? So this is the initial. This was initially point. Then you have moved to in the direction of steep descent with some alpha, training learning eta, sorry, learning constant, and then you moved here, like that, and finally you reach to this particular point. So minimum error. Okay. Now you can draw this graph can be projected in two dimensions, like MSC versus C and MSC versus M, right? Now what is the effect of learning rate? So what happens if the learning rate is too low and too high? So you can see the first graph. If the learning rate is too slow, it will require many iterations, okay, and many updates will be required in the weights, okay, before reaching the minimum point. So there are small steps are taken. Then if you are just taking just right steps, then it will swiftly reaches to the minimum point. And if your learning rate is too high, then what is happening? See, if you are at some point, okay, right? Suppose you are at this initial point, then you are moving. If learning rate is too high, you will may enter another end. Okay, then may shift to this end, like that. You may be just moving here and there, never reaching the final solution. Okay, so if your learning rate is too high, this happens. So this is called as a divergent behavior. Now, okay, basically I planned to tell you the coding of this, and for that purpose, what I have done, I have written here the equations. Okay, the first equation is the cost function or objective function, which is taken as mean squared error function. This is the most common one. You can take mean absolute error and many other functions. So this is the most used function. Okay, so we have described that. Okay, so here what is y bar? Actually, it is y cap. Basically, y cap means approximate actual output. Sorry, predicted output. Okay, so error means what? What was your say in this is a regression problem. Regression is supervised or unsupervised. Classification and regression are both supervised learning algorithms. Means what? If you are having the input vector x, okay, so then you also have, so the data is your data is labeled. That means if this is your input vector x, okay, associated with that you are having some value y which is labeled. And in regression you are having the real numbers, okay, like 1.52, 5.36, something like that. These are the numbers. Both positive, negative, and zero. All types of numbers are the regression. In classification, labels are the categories. Category 1 or category A, category B, something like that. Okay. So in the regression problem, you are having this number. So for every data instance, okay, or training example, you are having the label. So that is the actual label. Means suppose you say that, see, now if you want to predict, suppose take a problem of predicting salary from the CGPA. Suppose you have college का आपके पास में 2 साल का डेटा है, you have 2 years data, and you know the CGPA and you also know what is the salary that student got, and you train your model. Okay, so this is actually a particular student. Suppose this student has CGPA of 8 and he got salary of 4 lakhs per annum. Okay, so this is your x and this is your y. Now you suppose you are trained the model, okay, and suppose you give input as 8 to that model and you get the output as 4.2. Okay, what is the difference? This is called as the y cap and this is called as the y. Okay, so what is y? Y is the actual value for CGPA 8 is 4 and your model predicted what? 4.2. So there is an error. This is 4 and 4.2. So it will not be exact because your regression always try to find out the best value as per the training. Maybe because why this has got? Because maybe some other student also got 8 CGPA and he has maybe say 4.4 as the salary. Okay, and this model will then learn from many examples, not only from the single example. Okay, so that is your y. So the first equation is the error function. Okay, then substituting the value of y bar. Okay, so y is equal to what? Y cap. Sorry, y cap is equal to what? Mx plus c. Okay, so what is m and c? You will ask me. M and c is not yet found out. So what do? You have to initialize the model parameters with small values. So you have already initialized m and c to the small values, randomly initialized. That's why you know m and c. So these are initially random values. Okay, initially m and c are taken random. So y minus y cap. Okay, so what is y cap? Mx plus c. M and c we have just assumed something randomly. Okay, and we have found out the error. Right. Now what you have to do? You have to update the parameters. Which parameters? M and c you want to update. But how will you update? The update will be in the direction of slippage descent. So you have to find out the derivative, right? So derivative, calculate the partial derivative. You have to calculate the partial derivatives of the last function with respect to each of the model parameter. Now there are 2 parameters. So first we differentiate this equation with respect to m. Okay. So I have differentiated this equation with respect to m, and I have got. Finally you can work out at home. Okay. This if you differentiate this e with respect to m, and the term we got is suppose dm. Okay. So you have got this term, and if you simplify it, then it becomes dm is equal to minus 2 by n summation I equal to 0 to n minus 1. Actually it is x minus xi into yi minus yi bar. So xi is what? Ith data. Okay, ith data instance. Okay, remember. Yi means is respective output. Y cap means is respective output you have got. Okay, and y is the actual output. Okay, so yi minus yi cap means you are trying to find out the error between actual output and the predicted output at that instance. Okay. Now similarly you can differentiate partially with respect to c. That component is dc. So what is dc? Minus 2 by n summation yi minus yi cap. Okay, so this two dm and this u of I. Now this is what, these are the gradients. Now how will you update the m? Okay, you have to update the m in the direction of steepest descent, right? So this is m is equal to m minus eta, which is a learning constant, into the partial derivative of the objective function with respect to m, and c is equal to c minus eta into dc. Okay, so if when you do this, your m and c are updated. Now this will continuously go on, m and c will be updated till your objective function is minimized. Now this is just the animation for linear regression. You can see we have started from some initial line, okay, which is appearing from the down, okay, because we have taken very low values for M and C. So, and then gradually this particular data points is giving you best fit after some time when the algorithm is converged. So you can note the final values at sometimes 1.3 and 0.02, something like 1.4 and something. Okay, so this is how your M and C is continuously getting updated, and you finally get the best fit for this. Okay, now at this point I will just show you the code, which is very straightforward.
Desktop unit is used for also.
There is some problem with the projection. No. Now it is coming. Okay, so this is basically a Python code, okay, for the same. I will explain you the major steps. Okay, so initially you have done some imports, like say NumPy is imported. I hope basically Python is language which is known by everyone. Okay, so NumPy we have imported as library for doing the calculations with vectors and matrices. Then matplotlib is for plotting the graph, and okay, NumPy double हो गया. Now see what I have done here कि मैंने कोई डेटा कोई एप्लीकेशन का नहीं लिया, because I want to prove कि my जो रिग्रेशन के मेरे कोएफिशिएंट्स आए हैं या मेरे मॉडल के जो पैरामीटर्स है that I have evaluated correctly. Okay, उसके लिए what I have done, I have taken a random number generation. Okay, so I am taking my data as a random number generated. Okay, 100 random numbers, and then I have taken y is equal to 2x plus 4. देखो, this data is actually from where you get this data. This data you get x and y from the real world problem. X is what? जैसे आपने CGPA prediction का problem किया, तो you have to go to the T&P officer and take the CGPA of the students and respective salaries they have got. Okay, that data you have to collect from the T&P coordinator. But here I am generating randomly. Okay, x and actually I am trying to hit which line, y is equal to 2x plus 4. तो मेरा y जो रहता है y is equal to 2x plus 4 है, मतलब, and when I will find out finally I will show you that my m is 2 and c is 4. Are you getting? तो ये मैं निकाल के बताऊंगा. अभी x I have taken and y I have taken for the training data, right? Now what I am doing is that I am adding small random noise to simulate epsilon. I have talked about epsilon क्योंकि आपको जो डेटा मिलता है वो because of different reasons is not exact. Okay, so मैंने क्या किया कि y में मैंने एक random noise add किया, right? So you can see y is equal to y plus np into random rand n, मतलब normally distributed 100 random numbers in the range of 0 to 1 and that is multiplied by 0.1. मतलब मैंने और उसको कम किया, मतलब small values I am adding to the y to introduce the noise. So I want to show कि in spite of the noise, this particular algorithm is giving you the best line, right? तो y आपका मतलब जो है वो actual जो डेटा है वो actually y है. तो मैंने आपको बताने के लिए कि whatever I am doing, whether it is correct or not. Then see initial कहाँ से start होता है algorithm, you have to initialize the model parameters. So मैंने क्या किया? I have initialized one value to c and I have initialized another value to m. Okay, take initial values. Then I have taken some alpha because alpha is a learning constant. So I have taken it 0.1. You can take anything. You can vary the alpha and see what is the effect. Then the number of iterations are 1000. Okay, 1000 iteration maximum I want to give. You can make it whatever you wish. Then MSC threshold. MSC threshold is 0.01. That means when my error goes below 0.01, I would like to stop. Okay, stop doing the updation. And then I have taken n is the length of the x, means size of my data set. Right? How many data items are there? Training examples are there in my data set, that is n. Okay. Now what I am doing for I in the range of number of iteration, I am what I am doing, I am calculating prediction. अभी prediction क्यों बोल रहा हूँ मैं? Because I assume कि whatever is given m and c, okay, that is initialized parameters, I will get some line. That line may be wrong. That means I am getting some initial hypothesis which may be wrong, and because of that I will get some value, y prediction. So y prediction is equal to c plus m into x. Okay, y equal to mx plus c. So calculate predicted y. अभी ये करने के बाद what I have to do? I have to calculate the gradient. So I have taken directly whatever we have derived from. So this is a derivative of the objective function with respect to m. So we have seen that in the slide. dm is equal to 2 times sum of x into y squared minus y upon n. Okay, this is what we have taken here in this slide, if you remember. Okay, right? These are the terms dm and this is dm and this is dc. Okay, so these terms, so I have directly implemented them here. Okay, so this is dm is equal to this and dc is equal to this. Now I have found out derivative, partial derivative of objective function with respect to m and with respect to c. Now update the model parameters. So m is equal to m minus alpha into dl. Okay, so alpha is a learning constant. Alpha I am calling, there I have called it as eta. I am calling here alpha, doesn't matter. So textbook call it as alpha. So alpha or eta is a learning constant. Okay, multiplied by dm. So you are modifying m in the direction of steepest descent. Okay, minus because you are going in the opposite direction of the steepest ascent or gradient, opposite of the gradient direction. And c is equal to c minus this. This is also updated. So you have taken initial values, then updated this m and c. Then calculate mean squared error. Okay. So here MSE is equal to what? NP dot mean of y prayed minus y. So what I have done, NP dot mean means what? I have done this. So say I have updated the model. As soon as I update the model, what I will do, I will calculate the MSE over all the data points. So that's why it is mean. MSE is the mean of y prayed minus y. So it will. So what is y predicted? Y predicted is. So here what is y? Y is not a single value, you can see. Is y a single value? No. Is x a single value? No. X is a vector of values or array of values, and y is also an array of values. Okay, if there are 100 inputs, okay, dimension of x is 100. If I am, and same way y will also have the dimension of 100. So I am doing array processing. Okay, so that's why numpy is coming there, right? So here basically I am uh, so I am doing y pred. Y pred I have calculated predicted y vector. So y is not a y pred is not a scalar, it is a vector. For each value of x, I will get y pred, and all those value forms a vector y pred. So this is the peculiarity of Python. Actually इसके लिए C में करते तो इसके लिए for loop लिखना पड़ता था आपको, right? You have to write a for loop for doing vector operation. In Python you can directly do the vector operations. Okay. So this is for each value of x you have done calculated y value, and that y pred is now a vector. Okay. And here I am doing mean squared error. So np dot mean of this vector, okay, y pred minus y square. So ये सभी जो भी आपको y pred minus y का स्क्वायर मतलब you have got squared error, उसकी आपको क्या मिली? Directly mean over all the x samples. Okay. Then I am printing MSE, and then if MSE is less than or equal to threshold, MSE threshold, मतलब 0.01 I have taken as threshold, then I would like to stop. So I will say that converge in I number of iterations. Okay, I is my running variable. Okay, for loop variable, index variable, and then I am immediately breaking because my algorithm is converge because I have got the desired mean squared error. That is my stopping criteria. But I will maximum go up to 2000 iteration. So if even after going above 2000 iterations, if I do not get this, okay. So if MSE is less than or equal to MSE threshold, then I will print and break. I will break the loop. That means it will come out of the loop. Else I am continuing. This what the algorithm is not convert, and I will continue. Now after doing this thing, you may cross 2000 iterations. Okay, because you have defined that the number of iterations be num iterations, which is say 1000. Here I have taken I think 1000. So if when it crosses 1000, so what you have to do? Else print not convergent to the desired mean squared error. Okay, of this after these many iterations. मतलब 1000 iteration के बाद में भी converge algorithm नहीं हुआ है to the desired accuracy mean squared error. ये हम print कर रहे हैं. So this is a again peculiarity of Python. This is the for else statement in Python. Okay, so you can also write else statement for मतलब अगर वो कंडीशन false होती है तो it will come in for else. For else is in no other language. For else is in Python. You may not be knowing, but search it. For else is there. Okay. So this if is has else. This else is for. It's very peculiar. It's very funny and very valuable also. Now calculate the coefficient of determination. Okay, actually there is one metric, or you say performance evaluation, that is called as the R2 square. I will tell about that later on. So that tells you how close, how best fit is your regression, how good is your regression. Okay, so that factor I will tell you later on, which is called as the R2 square. So that also I am printing. And R2 score जो है, it is good. जितना fit अच्छा रहेगा, it will be more close to 1. So more the better your fit is, the line fit is, or you more better your regression is, the more more the value of R2 score will be. मतलब 1 is the highest value for R2 score. So if your R2 score is 1, means you have got the perfect fit. That is the meaning. So estimated parameters, then I am printing what is the value of C and what is the value of mu of R finally, and what is the final mean squared error and final R square value. And then I am plotting the graphs. Okay, scatter plot of x1 and then I am also plotting the regression line that I have found out. Okay, so that is the thing I am doing. So I am plotting the line for x and y predicted. See, I am not writing here y, but I am trying the line of y prediction because मेरा prediction कैसा है, सही है कि नहीं, that I want to plot. So I am not plotting x y, I am plotting x vector x versus vector y predicted. Okay, so the line will be drawn. So that is the basic line. Now suppose I run this particular algorithm, then you can see. Now see this was your data that was generated for the line y is equal to क्या था हमारा 2x plus we have taken some 2x plus 4 okay plus epsilon okay epsilon see because of that epsilon that I have introduced the noise in y equal to 2x plus 4 and because of that these points are not exactly on the line because I have deliberately introduced the noise into that data, and this is actually the case in practice. You will never get a straight line when you do regression, linear regression or practical problems. So to simulate that, I have added the noise into that. So you can see this is the best line you have got, and see now we'll see what is the mean square error we have got, right? So you can see 2x plus 4, so this is near 4. This line, if you see the y-intercept, it is near 4, and slope is near 2. So let us see this. Where is my output? Actually, I am not able to see that output window. Okay, actually it is supposed to display you. What I have done is that mean squared error, okay, in the for loop. Okay, so it will print mean squared error for every iteration, how it is decreasing from maybe very large value to the, at the end it will be less than 0.01. Okay, and graph we have also already seen. Okay, only these values I am printing. So where that window has gone. In the view. Okay. So this is your graph. Okay, we already see, and see this is the output. Okay. So they are all the MACs, right? So the MAC started from 36 and mean squared error then started decreasing because your MNC were getting more close and close to the actual values. And now at the end we can see our MAC is 0.0099, so it is less than 0.01, so it is stopped. So it is converging to 54 iterations only, although we have given maximum 1000 iteration. And estimated parameters are intercept C is 4.03C. Now it is very close to actual value of 4. Now why this 0.03 is coming? Because we have added noise in the Y. That's why there is 4.02, and then your slope was 2. So now it is coming as 1.96. Again, it is because of noise. If I remove the noise, I will get exact 4 and this. Okay, and MAC is 0.0099, and this R squared value is 0.97. Okay, so basically I told you that the value of R, which is the Pearson coefficient, okay, so which is very close to 1. That means your the fit is very good. Okay? Your fit is very good. So that also you can print. And if you remove the noise, okay, now what I will do? I will format this stage. Okay, I remove the noise. I will take y directly as 2x plus 4. Then what do you expect now? The value of y. MSA you expect very almost 0. 0 आनी चाहिए. R should be 1 because it is a perfect, it will be a perfect fit. And then what is else? M is equal to 2 and C is equal to exactly 4. So we'll run this. So it is very close now, right? Your line is very close to that, and your parameters. Actually, in this case, I can afford to change my MSC threshold as more because I know that there is a exact phenomena. So I do that, and let us see again, run again. See now, I have changed the minimum MSC threshold, and now it is exactly going over the point because the data was very correct. If the data is noisy, you will never get the exact fit. You will actually in practice you will not get exact. But here I am getting because I have taken the data like that, and because I have not added the noise, and you can see here the value of intercept 0.3.994, but it is almost 4. Okay, exactly. So you know that because of the floating point representation error also you will never get exact 4. Okay, but it is 4. Again here 2.001. It is exactly very close to 2, and MAC is also very small, 9.81 into 10 to the power of minus 8. It is 0 almost, right? And R square value is also 1. 0.99999 means it is 1, right? So because I have removed the noise. Okay, so this basically demonstrate this thing, and I will tell you something about measure of fit. Okay. Okay, so you have got some best some line. Now how good is that line? Okay, so how good is the regression line? So goodness of fit. So there is one metric for measuring this, and that metric is called as a correlation coefficient or Pearson coefficient R or P. Okay, so it is actually it can go between -1 to +1, and you can see that different examples. So here this example is P is equal to -1 means when your independent variable increases, the dependent variable decreases. Okay, decreasing trend. Right? You can see here this particular line. That's why it is equal to -1, and exact fit is there. Okay. Similarly, if P is equal to +1, that means as the independent variable increases, dependent variable also increases. and why it is exactly plus 1 means what? All the points are on the regression line. It's a perfect fit. So P is equal to plus 1. And this is also a perfect fit minus 1, but I mean, there is a opposite relationship in between the input and output variable. Minus means minus indicates that. Then this is if your this Pearson coefficient is between minus 1 and 0, then this is the case. This is between 0 to 1 is positive slope line. And see here the Pearson coefficient is 0. That means there is no linear relationship between input and output. Okay, all the points are scattered. No effective relationships or linear relationship is there. So there is no linear correlation between the input and output. So that is the meaning of that. Now, to simplify it, because many times we are not interested in the negative or positive, but just how good is the fit. So for that, okay, so this is the formula for calculating the Pearson coefficient. So this is Px y is equal to covariance of x upon sigma x sigma y. So covariance is the covariance between x and y. Sigma x is the standard deviation of x. Sigma y is the standard deviation of y. And the formula can also be expressed, and this covariance can be found out by covariance of x y is equal to expectation of x minus mean of x and y into y minus mean of y. Okay, and hence our covariance has so this is the formula, another version of the covariance. So you can calculate the P for the correlation coefficient with the help of the first formula given there. Okay. Then goodness of a fit for a linear regression. There is a R square measure. Okay. So what you do, whatever P or R you have found out, P is also called as R. So you take the square of that, it is called as a R square. So R square measure is the P measure or R measure is between minus 1 to give the values between minus 1 to plus 1, but R square gives you the values between 0 and 1. So it doesn't talk about the direction. Okay, it talks about how good is the fit only. Okay, so if you are having R square is equal to 1, that is a perfect fit. And what R we have got in our example, it is 0.96 or 0.97 somewhere. So that means you are very close to the exact fit, right? So your fit is, so if your fit is very close to 1, that is a very good fit. Okay? So if your fit is something like this, you can see the second graph, it is 0.5. And in the first graph, R square is equal to 0 because there is no correlation between input and output. Right? So that is the R square. Okay? So implementation we have seen. And then to extend this, the multivariate linear regression can be written like this. So when you are having more than one input variables, you can go for, or that problem is called as multivariate linear regression, MLR. Okay. So the equation for that is h is equal to y is equal to h of theta. H is called as a hypothesis because you can get many equations for the same problem, and one of the equations will be best. Like say y is equal to mx plus c, I have found out something, okay, like say 2.1 plus 4.01, something like that. Someone else may find out 1.99 plus 4.12, like this. Okay, so that means there are so many solutions, and one solution is the best. So हम इसको बोलते हैं कि hypothesis, which is called as a, there are many hypotheses, okay, which are near to the solution. So y is equal to h of theta, and suppose you are having two variables. So how will you write that equation? Theta 0 plus theta 1 into x1 plus theta 2 into x2. So x1 and x2, okay, that is by mistake square. Okay, it should be only theta 2. Okay, so theta 0 is equal to theta 1 x1 plus theta 2 into x2, right? Plus epsilon. So that is a noise. Okay, I will just it's by mistake actually. It's there. Because otherwise then it becomes polynomial regression. Right? Now suppose you have two predictors. Okay, suppose you want to find the salary, placement salary of the student, and you are having two variables, x1 and X2, which are CGPA and communication skill, and you want to predict. Okay. So basically, then you can consider this to be a three-dimensional plane in which there are two variables. Okay, and the third variable is the salary. On two axis you are having CGPA and communication skill, and third axis you are having salary. Okay. So if you go on increasing the parameters, then the problem goes in the hyperspace. Okay, you might be knowing two-dimensional space, three-dimensional space, and typically higher dimensional spaces are called as hyperspaces. Okay, and the equation becomes the hyperplane. In two-dimensional, say if your problem is two-dimensional, you want to predict x versus y, right? This is a two-dimensional problem, and you are having some line. Okay, so this is called as a line. When you are going in a three-dimension, the linear regression will take the form of the plane. Okay, concept of plane you might be knowing. And when you go to the higher dimensions, you are not able to visualize it as something, but it is called as a hyperplane. Okay, and if it is a non-linear problem, then it is called as a hyper surface. Right. So if you are having non-linear problem, then your this line may be a curved line, something like this. Right. This may be a curved linear regression. Okay. And in the higher dimensional space, it takes the form of a surface. Hypersurface, that is called. So hyperplane is for linear classification, I mean linear problems. Hyper plane is for linear problems. Hypersurface is for non-linear problems. Now see, why we should go for the gradient descent? You will ask, naturally you will ask question, and we have learned that machine learning should not be used when the direct solutions are available, right? Suppose there is some formula, then why you are going for training? You directly put the values in the formula and find out the output. Okay, so why should go for this gradient descent? So closed form solution for multivariate regression problem. Okay, so let us take a multivariate regression problem. So the goal is to fit a linear model with multiple independent variables, and model equation is y is equal to theta 0 plus theta 1 into x1 plus theta 2 into x2 up to theta k into xk, right? So the more the number of attributes you are having, those many number of parameters will be there, right? जैसे आपके इसमें y equal to mx plus c, if you take single x, there are how many parameters? 2 parameters. Okay, and if you take 2 variables, there will be 3 parameters because one is your intercept, right? So for every attribute you add, input attribute you add, there will be one more parameter that will be increased, right, in your model, right? So if you are having k number of attributes, then you will be having k plus 1 parameters, right? So the closed form solution for this is given by theta is equal to x transpose. So you now have a matrix X, okay? So how is the matrix? So see, suppose you are having the data, right? Suppose you are having a student data in which the first attribute is a CGPA of the student, second attribute is your what do you say, communication skill, third attribute is coding skill, and so on. Now suppose there are many attributes. Okay, so what is the first row indicates in this matrix? It is the first student. This is the second student, third student, fourth student. Okay, so you are having k number of attributes 1, 2, 3, 4, and these many rows. Okay, so maybe if there are n students, there are n rows, and if there are k attributes, there is a k columns. So this is a matrix of n by k. Okay, so the closed form solution is found out in linear algebra like this: x transpose into x inverse multiplied by xt into y. Okay, so why are your labels for that particular student? So what is y? Y is what? What your labels? So what are your labels? This y vector. These are the salaries that you already know. These are your already placed students, and you know their salary. The NP department has this data. This is the past data. Basically, machine learning train the models based on past data and predict the future. Right? So for some new student, you can predict the output. So these are the labels Y. These are the all the salaries. Okay, so this Y column, right? So so this theta is a column vector containing the coefficients theta 0, theta 1. So you will get what? Finally, what you will get? Theta means you will get the model parameter. So once you get the theta, theta means what? Theta is a vector. Okay, theta is a vector consisting of theta 0, theta 1, theta 2 up to theta 3. Okay, so once you find theta, अगर आपको theta मिलता है means what? You will get the equation. Because equation में what you don't know is theta, all the thetas. You know x, x1, x2. Suppose you have a given student, जिसके हमको salary निकालनी है. So you know about his CGPA. We know about communication skill. Suppose we measure the communication skill in the 1 to 10 range. You measure coding skill also in the range of 1 to 10, suppose. So all these factors you know, and you also know theta. How you have found out theta? By using this mathematical, your linear algebra matrix operations, okay, matrix inverse and transpose, right? So you have got theta. So once you know all the theta, you can find out y. So given student, you can predict his salary y, right? So this is a closed form solution. So x is a matrix, then x is a transpose, and y is a column vector containing the target values or labels that you already know because we have the data. So why prefer the gradient descent? Basically, कि gradient descent क्यों लेना है? तो directly हम matrix operation से कर सकते हैं. Data डाल दो matrix में, take the transpose and inverse and use that equation to find the theta. Once you get theta, you get the equation. Once you get the equation, input, give the input to that equation and you get the output. So why should go for that? So closed form solutions are good when data set size is small. That means the number of records you are having and is small and number of parameters are less. Now the number of parameters are depend on number of attributes. More the number of attributes that your problem is handling, more the number of parameters, right? So अगर वो small है तो you can use closed form solution. But when you go for the large complex problems, okay, when the data size is large and the number of parameters are also large, in that case your closed form solution becomes very time complex because you have to take the inverse of a very large matrix, which is having very high computational complexity, whereas gradient descent has very low computational complexity as compared to this. So gradient descent can be more scalable and efficient for very large data set. The closed form solution involves matrix inversion, which can become computationally expensive as the data size increases, especially if the matrix xt into x is large and memory intensity. So to hold that particular big matrix, you require a lot of memory because you know the real problems is what? There are thousands of data and hundreds of attributes. So the matrix becomes really very large. Now in case of online learning also, online learning, suppose your model is online learning, means something is happening, like say in, for example, your uh, real-time systems or able to swap. So your data is coming from the sensors, okay, and in real time, and you are trying to train the model. तो उसमें data आपके पास पूरा के पूरा at a time होता है क्या? Because it is time dependent. At some time you have got some data from the sensors. At second time you have got some data from the different sensors. So you can suppose there are 10 sensors. So each sensor can be called as one attribute. Okay. So you are having an input vector of 10 size. So at any moment you are getting 10 inputs from 10 different sensors. Right. So the closed form solution is useful when you are having the entire matrix available at your hand. अभी यहाँ पे क्या हो रहा है in real time? You are getting only one instance, only one row you are getting at a time, okay, at a particular instance, and you are going on training. So ये possible है क्या? Closed form solution में no, because you don't have the matrix at hand. But यहाँ पे आपको फिर कुछ wait करना पड़ेगा. यहाँ पे क्या हो सकता है? Gradient descent basically क्या करता है? It takes one data at a time and processes it and update the model parameters. So the moment it updates the parameters based on that single data, another data will arrive. So you can adjust the sampling rate interval so that as soon as this computation is complete, you take the next data, sample the next data from the sensors, and train the model in an online manner. So this algorithm also is beneficial there. So closed form solutions do not naturally support online learning because we don't have the matrix at hand in advance. समझ में आया? Now you may wonder how this can be extended to the multivariate problem. So it is simple. Now you are having a hypothesis, or your y is equal to h theta of x. So you are having n number of parameters. Okay, theta 0, theta 1, theta 1, and cost function is j of theta 0 to theta n. 1 by 2 m. Again, I am saying this because there are how many? Now see here n in this particular problem I have taken n for features and m for number of instances, training instances. यहाँ पे थोड़ा because ये जो ये था theta, okay, that was only there are only two theta m and c. तो वहाँ पे problem था. Now I know that there are n plus 1 parameter theta 0 to theta n. So वो n variable मैंने इसके लिए लिया और m I have taken for number of training instances. In the previous problem n was for number of training instances. Here there m is for number of training instances. So why 1 by m? Because we are taking average mean squared error, average of error over how many instances? M. So that's why m is there. And why it is 1 by 2m? 2 is for adjustment of when you take the partial derivative, that 2 square जो term है, it will come to the left and it will cancel out. तो उसको simplify करने के लिए people write it as 1 by 2m. You can write 1 by m as well. Okay. So algorithm is what? Repeat until convergence. You have to update the theta j, okay, and j is equal to 0 to n. So what is theta j? Theta means what? Derivative of basically how you have got theta by differentiating your this function, okay, with respect to theta j. Okay. So you are differentiating this objective function, okay, which is written as a mean squared error. That you are expecting with differentiating with respect to theta j, okay, and j is equal to 0 to n, right? So you can simultaneously update theta j for j is equal to 0 to n minus 1. So you will get those many number of parameters, theta 0, theta 1, theta 2 will be continuously updated because now there are n parameters. So these steps are actually n number of updates basically. In previous case there were only 2 updates, here there are n updates like this. Okay. Where I जो लिखा है देखो यहाँ पे you are getting the superscript I. Okay, so that is there for data instance I. Okay. So when you differentiate, you will get these equations and theta 0, theta 1, theta 2, like that. All the theta k will be updated, okay, and you will get this thing will continuously change until convergence, and you then at the end you will get the final values for theta. And once you get theta, you can find out y for any input x. Okay. So as I have told you, the gradient descent algorithm why is to be used. So basically gradient descent is a fundamental optimization algorithm used in various machine learning techniques to minimize the loss function and to find the optimal or best parameters for a best possible parameters for a given model, because output of machine learning algorithm is what? The set of parameters, because once you know the parameters you can find out the output. Okay, so finding best parameters is the objective of any algorithm. Okay, machine learning algorithm. Some of the machine learning techniques that utilize this are linear regression, Fourier polynomial regression, logistic regression, and so on. Okay, so they can use to find out, because every algorithm has some machine learning algorithm has some parameters to learn, and those can be found out by using the gradient descent. So whether you study neural network or support vector machine, and when these algorithms are implemented, this gradient descent is used to optimize the objective function and to find the best parameters. Okay. So here are the advantages and disadvantages of gradient descent algorithm. So it's a simple and easy to understand algorithm, efficient and can be used to train models on large data sets. That is the very good thing about that because we know that there are closed form solutions also available, but on large data sets, those become very slow. It is robust and can be used to train models with a variety of different loss functions. Loss functions can also be changed. Okay. Then it is versatile and can be used to train a wide variety of machine learning models. Okay. मतलब सिर्फ linear regression के लिए ही नहीं use होता है, as I have told you. Disadvantage is that it can be slow to converge, especially for models with many parameters. It becomes slow. It can get stuck in local minima. That is one more problem, and you have to take special efforts to take your algorithm out of the local minima. Okay. It can be sensitive to the choice of learning rate, which is the parameter that controls the size of the steps that the algorithm takes. So you have to experiment with various learning rates so that you finally come up with some best learning rate that gives the solution to the given problem. Now in conclusion, gradient descent is simple but powerful algorithm and is used to train a wide variety of machine learning models. And it is an iterative algorithm that starts with an initial set of parameters, initialize the parameters, and then repeatedly updates the parameters in the direction that will reduce the loss function. Okay. So this is all about from my side. So, any doubts you are having? Actually, I request all of you, I will give you the code, and if it is also I will share. You just try the code given, try with different values of learning rate, okay, that you can change. You can even pick with the MSC threshold, means square error threshold, and see finally what M and C you are getting, how it is varying. You can even change the data, you can change the equation, okay, all these things. Even you can take some problem, linear regression problem, and you copy that data in place of X and Y, okay, and try to run the problem. वो भी कर सकते हैं, because there is a code already given, just you have to pick with the code, and that is how you learn machine learning, right? So if you have a code, you can play with the code and see the output. Okay. So any doubt?
Well explained, sir.
I have taken, this is a simple algorithm, but I have taken it because it forms the basis for many advanced algorithms, and it is very important to learn it. So I thought when Madam contacted me, why not to teach this algorithm? Because many times there is a doubt in this algorithm. So I have taken this, and I hope you understood it. Yeah, I will mail you, or you can take it from here also. I have a folder that you can copy. This program is also.
We are sharing all the activities on the FDP group.
Okay, thank you. Thank you very much.
Thank you, sir. It was a great learning and having with you. All of us are very happy and very satisfied with your presentation. I would request Dr. Sir to please give a memento as to this.
Couldn't